All right, so this week, okay, as I just said, we're only going to look at one section, section 6.5. So what I've done, I just split it into two parts. Okay, so 6.5 is on solving right triangles. So we'll talk a little bit about what's a right triangle and what it means to solve it. But first, what's a right triangle?
A triangle that's 90 degrees.
Yeah. So you get a triangle with one angle that is a 90-degree angle. Is it possible for a triangle to have two 90-degree angles? No. What do all the angles have to add up to in a triangle?
180.
180. Okay, we can have other shapes with two right angles, okay, quadrilaterals and up, that's fine. But if you only have three sides, at most you can have one 90-degree angle. Okay, the side that's across from that right angle, or 90-degree angle, that's your hypotenuse. And how about the two other shorter sides?
Opposite and adjacent.
Okay, we're going to talk about opposite and adjacent. That's important. But in general, what do we call the short sides?
Legs.
Yeah, the legs. Okay, so I have a diagram. There's a right triangle, okay, marked by that symbol in the lower left. Put that little square there. Okay, generally, we use letters A, B, and C for the sides. Okay, where A and B are the two legs, and C is the hypotenuse. Okay. Theta, I just marked this right here. That would be an acute angle. Okay, we already said earlier why it has to be acute. It can't equal 90. It's got to be smaller than 90. Otherwise, the angles wouldn't add up to 180. All right, and next thing we're going to look at is a theorem that relates all the sides. Okay, we're going to look at what the theorem is and then where does it come from? Why is that what the theorem is? Which you may or may not have done before. So what's the Pythagorean theorem? Okay, and what does that mean? A squared plus b squared equals c squared. I get it in terms of this diagram, but pretend that diagram wasn't there. Yeah?
You take the sum of each leg, but you square each leg before adding it together, and it should equal this, and it should equal the square of the hypotenuse.
Yeah. Okay, so the basic idea behind the Pythagorean theorem, you square one leg, square the other leg, add them up, and that's equal to your hypotenuse squared. Okay, whether you want to call the sides A, B, C, X, Y, Z, whatever you call them. All right, how many people know where that comes from? Like if I asked, why does A squared plus B squared equal C squared?
Because now.
Because now. Has anyone ever seen the explanation of it? Yeah?
Does it have to do with like it being put into a square?
Yeah, it does. There's probably 100 different ways to show where it comes from, but one of them is making a square, and we're going to make a square and look at that.
It's also from the factor that that's only the case if it's a right triangle. If it's not a right triangle, then it could be possible for Pythagorean theorem.
Right, that's important too. Okay, everything we're doing today only applies to right triangles. Okay, so we should write that. This is for right triangles. Okay, if you have a non-right triangle, there's a formula. There's a couple other formulas we can use. Okay, one of them is called the law of sines. The other one is the law of cosines. We're not going to look at those today. All right, so what I've basically done down below is I took this triangle, okay, and I made 4 copies of it. Okay, so here's one copy. There's second copy, third copy, and fourth copy. Okay, and if you make all those triangles and they're all congruent, okay, arrange them the way I have, you get this square in the middle. Okay, and you get a big square on the outside, yep. So you get really there's 2 squares there. Okay, any questions on that diagram? Okay, and the whole goal of proving the Pythagorean theorem this way is to find the area of the square on the inside. And you got to find it two different ways. Right, so let's just put this in red. So this is what we want to find. Right. Somebody give me a quick way to find the area of that red square.
C squared.
It's c squared. Yeah. Just take length times width, and that's the area. So we'll call this area of red square, and we'll call it the first way to do it. Okay, we get c squared. Any question on that?
Why did you put the 2 there?
You're right. Why don't we put it like that?
Is that a valid question?
So, any questions on that? Okay, now, what's another way we could find the area of that red square?
C times C.
Yeah, so that's what we have here. Yeah.
Let's go down.
Maybe sometimes the other C.
Want to think in terms of this bigger square and these triangles. Yeah?
Find the area of the big square and then subtract the area of the 4 triangles.
Yeah, you could find the area of, let's just write that out. So find the area of big square, and then subtract the 4 triangles. Okay, that's going to give us a different formula, but it's going to be equal to the first one. Okay, it's the same shape, so it has to have the same area. Right. So what's the area of that big square? Not AB times AB, close. We are going to use the A and the B though, but yep.
It'd be A plus B squared.
Yeah, it would be A plus B squared. Okay, because we have A plus B is the length of each side. So multiply A plus B times A plus B, and that's A plus B squared. And now, what's the area of one of these triangles? Yeah?
Of 1?
Yeah, just one of them.
1 half A times B.
1/2 A times B. And they're all congruent. How many of them do we have?
4.
We have 4. All right. So now, what do you get when you FOIL out A plus B squared? Brian?
I believe it's A squared plus B squared plus 2AB.
Yep. Okay, so when you FOIL that out, you get A squared plus 2AB plus B squared. And what's 4 times 1/2? 2AB. And what's going to happen there?
AB squared. The 2AB squared.
Minus 2AB plus 2AB.
That's A squared.
So this is another formula for the area of that square. Now, if this one and this one are both the area of the same shape, what can you do with them? Yeah, set them equal. So then we get the Pythagorean theorem. Okay, so that's one way to prove it. Okay, again, there's probably 100 different ways you can do it, but this one's pretty straightforward. Okay, any questions on that? All right, so keep the Pythagorean theorem in mind. We'll be using that, along with the fact all the angles add up to 180. Okay, that fact will be important too. All right, so now we're going to define the 6 trig functions in terms of some special words. Okay, we're going to use the words opposite, adjacent, and hypotenuse. Okay. Does anybody know what the sine of an angle is? Yep, opposite over hypotenuse. How about cosine? Adjacent over hypotenuse. Good, yeah. Then tangent's opposite over adjacent. Okay, we've looked a little bit at the unit circle, okay, and we did it that way. This is really the same thing. It's really exactly the same thing. Does anybody remember what sine was when we did it on the unit circle? It was equal to a letter.
Y.
It was y. How about cosine?
X.
It was x, and what was tangent?
Y over X.
Y over x. Okay, let me show you. It's exactly same thing. Okay, if you had unit circle. Okay, what's the radius on a unit circle? 1. 1. Remember, radius is a length. So just 1 unit, whatever, 1 inch, 1 foot. A radian would measure an angle. Okay, but a radius is just a distance. Right, so let's make a triangle right there. Okay, let's give that point coordinates x, y. Okay, you go right x, up y. That's x, that's y. If I put theta right there, what's my hypotenuse of this triangle?
X squared plus y squared.
1.
Yeah, we could use the Pythagorean Theorem, but in this case it's a unit circle, so we know it's 1. Okay, now look at, okay, sine is opposite over hypotenuse. What side is opposite theta? Y. And what's the hypotenuse?
1.
So that's why sine is equal to y. Okay. Cosine, that's adjacent over hypotenuse. That's why we had x. Okay. And then tangent,
Opposite over adjacent.
opposite over adjacent. So whether you use the unit circle definitions like this, or you use the opposite and adjacent hypotenuse stuff, it's the same thing. Okay, it's exactly the same thing. All right. What are we going to do with our 3 trig functions on the left to get the 3 on the right? Yeah, flip them. Okay, so the cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. Okay. One thing, make sure we understand about using the terms opposite and adjacent is they're what I call relative terms. Anybody know what I mean by that? They're relative terms. Yeah.
Are they based on a reference point?
Yeah, they're based on a certain point, just like left and right. Okay, left and right is based on your perspective. So if I'm facing you, left is the door, right is the windows. But if you're facing me, left and right are switched. So right is the door and left is the window. Okay, so they're relative. Okay, and what they're relative to, as Aiden just said, is a reference point that we call theta. Okay, depending on where you put theta in your triangle, think of theta as where you're standing. Okay? If you're standing here, opposite is what's farthest away. In this case, y. Adjacent is what's right next to you. Hypotenuse, that's more of an absolute term. It never changes. Hypotenuse is always across from the 90. Doesn't matter where you put theta. Okay? That's like for all of us saying up is the same direction. Okay? It doesn't matter which way we face, as long as you're standing on your feet. Up is always the same direction, and so is down.
Is it really? What if you're like in a handstand?
Well, if you're not on your feet, then. Yeah.
If you're in a handstand.
But you got to be standing on your feet.
But
Okay.
like, technically still be up, you're just upside down.
Well, again, it's no. I don't think of it that way.
Oh, I have to understand.
All right. So if you've got 2 right triangles with all the angles congruent, that means that they are similar. Okay. So all of the trig functions that we work with, it doesn't matter the size of the triangle. Okay, if you have 2 triangles that are similar, the trig functions are always going to have the same value for a given angle. Okay, for example, here's 2 similar triangles, not congruent, but similar. Okay, Okay, they each have the same angle. They're both 30, 60, 90 right triangles. And let's find the sine of 30 degrees in the smaller one. Let's find it in the bigger one. And I'll show you that they come out the same. Okay, what would be the sine of 30 in the small triangle? Brian?
1 over 2.
Yeah, 1 over 2. Opposite over hypotenuse. How about the sine of 30 in the bigger triangle?
2 over 4.
It's 2 over 4,
1 over 2.
which becomes 1 over 2. Okay, so what I'm trying to show you is it doesn't matter the size of your triangle. The sine of 30 is always the sine of 30. Doesn't matter the size. Okay. Any questions on that? All right. All right, so how do we find the 6 trig functions? Okay, if you're given one of them to start. I'm going to give you a problem like that. I'm going to tell you that the sine of an angle is 5/6. What do you know just by this fact right here? It tells you enough information that you can find the sine, the cosine, the tangent. You can get everything you want.
Tells you the ratio of the opposite side to the opposite.
Yeah, wherever we put theta, we know the ratio of the opposite to the hypotenuse. Okay. So what we're going to do is take the information that we're given, and it's going to be enough to label 2 sides. In the case of what Aiden just said, the opposite and the hypotenuse. And then if we know 2 out of 3 sides, yeah, you could just use the Pythagorean Theorem to find the 3rd side. And now you have all the sides in the triangle, so you can find anything you want. Okay, so you're going to label 2 of the sides, use the Pythagorean Theorem to get the 3rd side, and then you can find anything you want to find. Okay, so any questions on that? All right, so let's try an example. All right, so this one says the sine of theta is 5/6. Find the values of all the trig functions of theta. Right, and I'm going to make an assumption here about what quadrant I'm in. What quadrant do you think I'm in here? Yeah, I'm going to assume that I'm in quadrant 1. Okay? Because they wrote the opposite side is positive and the hypotenuse is positive. Now, there's another way sine could be positive. If you were in quadrant 2, okay? Pretend you drew a triangle in quadrant 2. Okay? I'm going to think of sine as, think of it as the y value. Okay? Think of it as the unit circle. The hypotenuse, on a unit circle, it's always 1. Is the y value positive here?
Yes.
Yeah, you went up. In quadrants 1 and 2, okay, when you're doing the y value, you go up for both. Okay? So technically this information only says I could be at the point, let's see, well, we don't know x, we know y is 5. Okay, so I'm up 5. I just don't know, is it right and up or left and up? Okay? I'm going to assume, though, that I'm in quadrant 1. Okay? Because if we assumed we were in quadrant 2, then what kind of value would we get for x?
You have a negative labeling.
Yeah, we'd have negative for x, which is fine. Okay, you can have a point in quadrant 2. Okay, but for this problem, let's assume quadrant 1. Plus, if you think about the kind of triangles we're working with, what are we limited to with angles? What's the biggest we could have an angle be in a right triangle? 90. Here's 0. Here's 90. Okay, so I have to be somewhere in quadrant 1. Otherwise, if I sketch an angle in quadrant 2, okay, now I've just drawn a triangle that would have an angle more than 90. Okay, that is possible, but not for the kind of problems we're doing. Okay. So, any questions why we're going to be in quadrant 1? All right. All right. So, how would I set this up? What do I have to do first? Yeah, let's just draw a triangle. Make it a right triangle. What should I do next?
Place theta.
Yeah, place theta. Does it matter where I place it?
Not really.
No.
Place theta is not drawn to scale.
Yeah, we can put it at the top or we can put it on the right side at the bottom. It doesn't matter. Now it matters where we put the 5 and the 6. Where's the 5 going to go?
At the bottom.
Right, opposite. Once I decided where I'm going to put theta, I got to put 5 opposite. What about the 6? Hypotenuse. And how do I get the side I'm missing? Pythagorean Theorem. Okay, so Jacob, what's my equation to find A here?
A squared plus 5 squared equals 6 squared.
All right, so we're going to get A squared equals, that's going to be 25, that's 36. What's 36 minus 25? So A is, yeah. Now, depending on the type of problem, they may have you round it, they may have you leave it exact. Well, it just says find all trig functions, but let's do it exact. Okay, so we've got the sine. Let's find cosine. Okay. What's the cosine of theta? Yep. Square root of 11 over 6. And what about tangent? 5 over the square root of 11. And that would clean up to square root 11 over 11. Yep. All right, so we got our sine, cosine, tangent. What else do I need to find?
Cosecant, secant,
Cosecant, secant, cotangent. Okay, what's my cosecant?
6 over 5.
Yeah, just take the sign and flip it. 6 over 5. How about my secant?
6 squared root of 11 over 11.
6 square root 11 over 11. Good.
Square root of 11 over 5.
Yep, it's easier to go back and just flip the first one
Square root of 11.
and get square root 11 over 5. Okay, so any questions on finding all 6 trig functions given any one of them to start? Okay, it doesn't matter which one they give you to start. You're going to have 2 numbers. Use those 2 numbers to label your triangle and figure out everything else. Okay, this one they kind of started you off with the first step. Okay, what trig function did they really give you here?
Tangent.
Yeah, they're really telling you the tangent is 5/12. Okay. What's the hypotenuse here?
13.
It's 13. Does anybody know what you call that kind of triangle? Yep, it's a Pythagorean triple. Okay, 3, 4, 5 is another one. 5, 12, 13. Those 2 come up a lot. There's infinitely many. Okay, and when I say infinitely many, I'm not counting multiples of like 3, 4, 5. So like 30, 40, 50. That's still 3, 4, 5. Okay, it's just everything's 10 times as big. Okay, but that's a Pythagorean triple. What's nice about that is now we don't have any square roots. All right, so Dominic, what is my sine?
5 over 13.
5 over 13. Yep. Kanan, what about my cosine?
The cosine would be 12 over 13.
Yep, 12 over 13. Dave, my tangent? Let's see. Yep, 5 over 12. Ashley, my cosecant?
13 over
Yep, just flip that, 13 over 5. John, my secant?
13 over 12.
Yep, 13 over 12. Okay, and Derek, what about my cotangent?
What is cotangent again? I don't remember.
Adjacent over opposite.
It was 12 or 12 over 5.
12 over 5. Okay, so any questions on that one? When would you have a trig function and flip it come out the same?
It's a whole number. When it's a 45, 49, 9. Oh.
Yeah.
Okay, actually, yes, that'll happen in a 45, 45, 90. And we're going to talk more about that in a second. But what number could you flip and it would stay the same?
1,
1
-1,
or -1 if you happen to get a negative. Okay, since we assumed quadrant 1,
just 1.
okay, they're all positives. All right, so let's take a look and see if we can figure out the 6 trig functions for a 45, 45, 90. And because it's a 45, 45, 90, that's isosceles. So 2 sides are the same. I could scale this triangle as big or as small as I want. Okay, because does the size matter? No. I just picked ones because those are easy numbers to work with. So what's my hypotenuse here? Square root of 2. So is this triangle on the unit circle?
Yes.
No.
No. Okay, the hypotenuse here is 1.4. It's a little bigger than the unit circle, but that's because of the sides I chose, 1 and 1 for the legs. All right, so now if I want to find the trig functions for 45, does it matter which acute angle I use as my reference point? No. They're going to come out the same. So let's just use that one. So James, what's the sine of 45?
Square root of 2 square root of 2 over 2.
Yep. So you'd have square root of 2 over 2. Yep. Okay, so no 2 in the top here. That's my sine. Nick, what about my cosine? Yeah, same thing. Okay. Since opposite and adjacent are the same, sine and cosine are the same. Okay, and what about my tangent? 1 over 1. Okay, or just 1. Right, so those are the 3 main functions we use most of the time. Now we'll find the other 3. What's my cosecant?
Square root of 2 over 1.
Yep. Just square root of 2 over 1. How about my secant?
Square root of 2.
Yep. Oops, let me put in 45. 5. Square root of 2. And my cotangent?
1.
1. Okay, as we just said, when you flip 1, it stays 1. Okay, so any questions on the 6 trig functions for 45, 45, 90? All right. So now I want to use this diagram somehow to figure out the 6 trig functions of 30 and 60. Okay, what kind of triangle is that? It's equilateral. And what does that mean? It means a few things, but yeah.
All the side lines are the same.
Okay, all the sides are the same. What else does it mean? All the angles are the same, which means they're all 60. Okay, each angle, each vertex here makes a 60-degree angle. So what could I do here to create a 30, 60, 90 right triangle? Yeah, you could split it in half. Okay, we're not going to prove using geometry why, but if you draw a segment down from that top vertex, this segment is all kinds of things. It's an angle bisector. It's a segment bisector. It's an altitude. Okay, and that's all because it's an equilateral triangle. Okay, so now this is a 60, and this is a 30. Okay, and what I'll do is just off to the side, just make a copy of half of that diagram. What's the length of this bottom side? 1. Okay, because I said this is a segment bisector, so if the whole side is 2, that side is just 1. That's 2. And what's the height of that triangle? Square root of 3. Right. So now we can go through and find our 6 trig functions of 30 and 60. And what's nice is we can use the same triangle for both. Just change your reference point. Right. So let's just do the first 3, the sine, the cosine, and tangent. So what's sine of 30? Yep, that's a half. Okay, cosine of 30. Let's see, square root of 3 over 2, yep. And the tangent? Yep, it would be 1 over the square root of 3. Okay, because remember, this is our reference point, so opposite is 1. Adjacent is square root of 3. And then when you fix it, square root 3 over 3. All right. Anybody need me to do the secant, cosecant, or cotangent? All right, so let's do it for 60. What's the sine of 60? That's square root 3 over 2. What about cosine of 60? A half. And tangent of 60? It would be, so the tangent is opposite over adjacent. Remember, that's our point of reference now. So square root of 3. Okay. What do you notice about, just look at the sine and the cosine. They switched places. Okay. Had we done all 6, the sine and cosine would switch, the secant and cosecant would switch, and the tangent and cotangents would all switch. Okay, so when you're dealing with the 30s and 60s, it's all the same numbers. They just switch places. Okay, because all you're doing is switching your reference point. So opposite and adjacent switch. Okay, any questions on that? All right. So I'm going to focus on that in a little bit. So just as a reminder, if you have angles that are complementary, that means they add up to 90. And I'm saying that in a right triangle, the 2 acute angles are always complementary. Why? Right?
Because you already are given a right angle which is already 90 degrees when the entire triangle's, the sum of all the interior angles of the triangle is 180.
Right. Okay, so all of the angles have to add up to 180. If the right angle already uses up 90, then the other 2 angles have to add up to 90. Okay, so we could write, why is this true? Since all angles add up to 180, and the right angle angle is 90. The other two angles are also 90. Add up to 90. Other two angles must add to 90. All right, so when we start solving triangles, okay, this is the diagram that we'll generally use. Okay, for the sides, I use what we always use, lowercase a, b, and c. For the angles, I use two Greek letters. I put a across from alpha and b across from beta. Now, in trig, my book uses the Greek letters. Our book doesn't use Greek letters. They use capital letters for angles. Why do you think that could be a bad idea? To use capital letters for angles and lowercase letters for sides.
It could get confusing if you forget to capitalize.
Yeah, so now, when we're talking about something, if you say, well, I'm not sure how you got A, well, you mean capital A or small a. And even with the letter C, it could be confusing if you have a capital C or a small c, they look the same. All right, so what we'll do is use capital letters. We won't use capital letters. Greek letters for angles, lowercase letters for sides. Okay, but if you see problems in the homework, which you will in the book, just pretend capital letters, we're using Greek letters. Okay. Any question on that? Okay, but it is good to understand, both ways of writing it. All right, let's look at a couple trig functions here. Okay, let's do the sine of alpha. Brian, what's the sine of alpha there?
A over C.
A over C. Okay, now let's find the cosine of beta. What's the cosine of beta?
A over C over C.
A over C. Okay, so notice, again, those two come out the same. It's kind of like what we just did with the sine of 30 and the cosine of 60. Right? Let's do tangent of beta.
B over A.
B over A. And then let's do the cotangent of alpha. That's also B over A. Because remember, cotangent is adjacent over opposite. So from this perspective, adjacent is B, opposite is A. Right, and we could keep going. We could do like secant of alpha, cosecant of beta. I could do sine of beta, cosine of alpha. Okay, this type of thing is going to keep happening. And it's called the complementary angle theorem. Okay, the complementary angle theorem says that cofunctions of complementary angles are equal. Okay, so your cofunctions are things like sine, cosine, tangent, cotangent, secant, cosecant. It's a different way to pair trig functions up. Okay, we've always paired them up as reciprocals. You flip one to get the other. Here, you're just saying a trig function, and then putting the word co in front of it. Sine, cosine. Tangent, cotangent. Secant, cosecant. So as long as you have two things, cofunctions and complementary angles, they will come out exactly the same. Right, so using that idea, who can tell me what the sine of 10 degrees would be the same as? What would the sine of 10 be the same as? Jacob?
The cosine of 80 degrees?
Yeah. So first he found the cofunction, and then he found the complement. Okay, so the sine of 10 and the cosine of 80 are exactly the same. Right? And we can use those kind of facts to help us simplify something like this. Okay, I want to know what the sine of 35 minus the cosine of 55 is.
It would be 0.
It would be 0. Okay. Notice here, what are sine and cosine? Those are cofunctions. And how about 35 and 55? Complementary. As long as you have cofunctions of complementary angles, they are equal. Well, if you subtract two things that are equal, you get 0. Okay? The wrong approach here would be to try to figure out what's the sine of 35. Okay, I don't know what the sine of 35 is. It's a decimal and it's pretty messy. Cosine of 55, it's another decimal that's pretty messy. But I know they're the same. That's all I need to know. And when you subtract two things that are the same, you get 0. Okay, how about the tangent of 20 divided by cotangent of 70?
1.
Yeah. Cofunctions, complementary angles. Again, the top is pretty messy, the bottom's pretty messy, but I know that they're equal. They're the same thing. Okay. Divide two things that are the same, you get 1. So with these kind of problems, the only way you could get an answer other than 1 or -1 is if you put in a +3 or a ×2. But what's in the parentheses here, what's that equal?
1.
That's 1.
5.
The answer is 5. Okay. Now, if I changed 15 to 14 degrees, could you still do it without a calculator? No. Okay. Now that theorem doesn't work. Okay. It's got to be cofunctions, and the angles have to add to 90. Okay. Any questions on that? Okay. So that's your complementary angle theorem. All right, so that's good for the first half of 6.5. We'll finish 6.5 tomorrow with solving triangles. Okay, we'll actually find out how long are sides and how big are angles in a triangle. Okay, so on 361, try 1 through 14, 16 to 20, just the evens, okay, 21 to 24, and I want you to just simplify these two problems. Sine of 40 divided by cosine 50. Tangent 35 minus cotangent 55.